Okay, so we're talking about time-delayed systems, and we're going to use some frequency domain thinking to talk about this. So let's look at some examples of time-delayed systems. This is one temperature-controlled laboratory apparatus. I put this here because when I was doing control systems way back when I was at university, which is a few years ago now, nearly 30 years ago, scarily, this is what we did for our lab, and it's basically demonstrating this issue of temperature sensitivity. I'll come back to this, but what this is representing is basically a pipe. It's like a PVC pipe through with a fan in it, pushing air through a heater, and the airflow, of course, is heated up like a, basically like a resistive heater in a car or something like that. And then there are thermistors at 3 points, and you have to connect each thermistor in turn to this loop. So you could connect it here, and of course the time between a change in the voltage to the heater and the impact on the temperature of the airflow that's measured by the sensor is going to be less than if you were using this one, which is further away. So this is basically looking at the impact of time delay between a control action in the heater and the sensed output at the thermistor end, and that goes back through a sort of a comparator between the input. This is your set point here, and you compare that. The error creates a gain, and the gain controls the plant voltage. So that's this situation. Another nice example of time delayed systems in a combustion engine. Of course, combustion engine is going to be a thing of the past just now, but for now we could just about still use this example. So the combustion process, it takes place, of course, in the chamber here. The air-fuel mixture, the charge air, flows in through the inlet valve, gets compressed, and is often the piston itself, the piston head, will have some formation that creates turbulence here. Then you get a spark, and the spark creates, the combustion event, pushing the piston back down. Then on the next stroke, if it's a 4-stroke, it pushes the exhaust gases out here. And over here we have what's called a lambda sensor. This lambda sensor measures the oxygen level in the exhaust gas, and that oxygen level is directly correlated to the stoichiometric, well, let's say the air to fuel ratio of the combustion mix. If it's stoichiometric, you should have basically 0 oxygen, but if you've got excess oxygen, it means you're probably running a lean mixture. If you've got an oxygen deficiency, you're probably running a rich mixture. So the issue here, though, of course, we're talking about it being a time delayed system. It's time delayed because there's a transportation time again as the exhaust gas exits the piston, the cylinder, and travels down the exhaust manifold until it reaches this sensor. And sometimes you have a close coupled lambda sensor, which means it's on the exhaust manifold itself, but often you also have a lambda sensor which is in the exhaust pipe somewhere further down inside the vehicle. So in that case, it would take really quite a while for the sensor to pick up if there is something going wrong in combustion. Right, if the air-fuel mixture is off and the AC, the electronic control unit of the engine, would have to compensate. So whilst we're talking about this, it's an opportune moment for me to conduct this little totally unassociated poll. This is it. Give me a second to type it in here. There's only 41 of you. I was hoping to get a poll with more, but let me ask this question. Would you be interested in taking a motorsport elective if it was offered in the final year? Right, so let me see how many people respond to this I know some of you might be into Formula One and this kind of thing. There are some of us in the faculty who are also into motorsport, into Formula One, especially. So we could use some of that, and the thinking being that there's so much technology in those vehicles that we could really use it apart from teaching about motorsport. It would allow us to sort of reinforce with application a lot of different technologies that the vehicles would carry. And I think this would sit probably inside the energy stream, or possibly in the energy stream. Yep. All right, so I got a few responses. So it seems like maybe about 2/3, 1/3 split so far, in terms of who'd be interested. So, okay, we'll bear that in mind. And it's really Mr. Matabadal, who is like super ultra into F1, and he loves the technology. He loves all the engineering behind it. That's what keeps him very interested. So, and I'm also, of course, automotive background. I'm a keen fan of motorsport and Formula One. So between the two of us, we will look at doing something. All right, so that was just a complete aside. But it's interesting to canvass some opinion. All right. So as I said, this is an example of transport delay because the lambda sensor, which measures the oxygen content of the exhaust gases, is located away from the combustion chamber. And this is another example. We used to have a steel mill in Trinidad. Unfortunately, it closed down. That's Mittal Steel in Point Lisas. And so we used to have this as an actual live production process in Trinidad. And this is the formation of sort of steel plates, or steel panels, or whatever it might be, sheet steel. And the way the steel comes in hot and is compressed by some rollers, so the force on these rollers, of course, will determine the gauge of the steel that comes out of the this process. And you want a very consistent gauge or thickness of the steel. So you actually have a measuring device, but of course this measuring device can't be too close to the rollers. Why not? Because the steel strip is rolled at a very high temperature to make it malleable. So you have to have this gauge a little further downstream. And of course, by the time you're measuring an error in your gauge, which allows you to correct the pressure or the load on these rollers, then substantial amounts of steel plate could have, or steel panels could already have been defective. So this is another example of a time delayed system. So as we see it in quite a few systems like this time delay systems, the delay really comes in the measurement of the output of the system. Here's another one, a pilot in an aircraft context. Now, in this case, it's not the output that's being measured. The pilot is responding to an error. So the pilot is basically a person in the loop in this situation, and the pilot is assessing visually the error between the demanded whatever it is, it could be pitch or altitude or whatever it is, and the output, the current state. He's manually assessing that and making adjustments on the control stick to control the aircraft dynamic in manual mode. But pilots, like all humans, have inherent time delays called reaction time. Right, so a pilot has reaction time, and reaction time is typically about 0.2 of a second. And so your pilot could be modeled as a time delayed control system with a gain KP, which is the sort of his response to the error, and then this term e to the minus s tau, and that represents the time delay. So if you replace the tau with 0.2 in this case, then that shows what the kind of time delay is. And we'll come back to, we got this from Laplace from lecture 2. We showed that any system, if you have a system that's time delayed, and you take the Laplace transform of that system, and we're going to come back to this in just a minute because I've got another slide that shows this. We take the Laplace transform of that system, then that's going to be, I think, fe to the minus s tau, right? Tau being the time delay. So that's where we get this exponential term with the s in the power that represents this pure time lag. So what might happen is that if you're in very high or very fast response maneuvers, then that additional time might, the lag time might actually cause oscillations or instability in the dynamics of the system, the dynamics of the aircraft in this case, because the reaction time is too long. So by the time the pilot is starting to react to a condition in the aircraft dynamics, then the aircraft dynamics will have started to change before you can react back. Right, so we'll look a bit more at that in just a minute, how that can create instability. So let's think about a time delay system generically. So we have here a system with an input on the left side going through our block, and our block now has three components. It has a proportional gain, a first order lag, and now we also have our pure time response. And so this element is our pure time response, which we factored into our transfer function in this block. Right, and we said that e to the minus s tau term represents this pure time delay, and this is where it comes from. This is just again a reminder. I wrote it on by hand on the last slide, but this is where I have it in the slide, that if we have a system that has zero outputs for time less than 0, but then for time greater than time t, sorry, zero output for time less than t, which is a lag time. So the system has no output up until, not 0 in this case, but has no output up until some lag time t, and then above that it has a function, basically it behaves like f of t, but lagged by this time constant, this time lag t. So the shape of the curve will be the same, it's just translated by t seconds, right? And that's for times above this lag time. And then if you take the Laplace transform of that, so we're going this way, and we transform this function g of s of f, taking the Laplace transform of ft minus capital T, then as I put above in the previous slide, you get this e to the minus st term as well as the f of s term. Right, so this is a graphical representation of what we're talking about here. So we're dealing with a first order system with a time delay. Just an open loop response here, but you can see clearly, if the input is at 0, then the response is literally the right shape, but it's just lagging by this tau. If we have a small time this delay, we might get something like this, and what happens is that if it's an open loop system, you just get the, because there's no feedback at all, so literally the response is just translated and delayed by the time, tau. If we introduce a closed loop response, we're going to find that what happens is you get a slight degradation in stability, so you get a faster response to the input, but you get this overshoot and settling time if you have a small time delay. And if you have a large time delay, that's just going to amplify the overshoot and settling time, right? So that's the effect of this pure time lag on a system when it's running closed loop. The larger the time delay, the greater the instability or relative stability degradation that's going to take place, which is what you're seeing in the bottom right chart there. You're seeing the relative stability degrading, getting worse. The system becomes more oscillatory. The time responses show that increasing the time delay can degrade stability, and although this can be analyzed using frequency response methods, it can be explained as well by just considering the dynamics of the system. Right, so we're going to come back to my lab experiment. I told you I'd come back to this and go through it, think about the logic in this system and what's really happening, or like physics of the system, if you like. So let's think about this again. And here we're dealing with a controller gain which is fixed, so the gain inside here, we'll just call that K, it's not changing. What we're dealing here with is just the distance of the thermistor from the heater, right? So that's the only factor that's changing in this particular experiment. We could represent this system as a block diagram, and if we do that, then our input, which is shown at the bottom here, that becomes our input on the left, right? We have the comparator, which is this part here, comparing the current temperature measured by the thermistor with the input. So this is our thermistor here, which is comparing our current temperature output with our input to give us an error, right? So we're dealing with an error ET. If we apply a step input to this system, and we're applying a step input at this end here, we'll call that. And if at the point at which I apply that step input, assuming ambient temperature is 20 degrees C, right? So the output will be at 20 degrees C. So if I just sketch this on here, and I'll say I'm introducing an input of a 50 degrees C input, so I want the air in the pipe to be coming through at 50 degrees C, but at the point at which that step input is applied, you know, the output's still going to be the ambient condition 20 degrees C. So you're going to get a large error. You know, maybe this will be 30 degrees C error at this point. And that's going to mean that you get a large control signal, probably close to max or close to the saturation of your voltage output from that control system. And that means that you're going to get if you get a step change basically, or a large ramp in your control action, then you're going to get a large ramp in your heater voltage and a large ramp in your fan speed. So both of those are going to go up. The increased air temperature that results from those will not be detected until, of course, it's been transported to the sensor. So it has to get here to the sensor before that ramp, fast ramp in output temperature is observed. As you can see here, it's like it has to flow from here, you know, especially if we're dealing with this last thermistor, it has to flow all the way here. That's going to take some time, some number of seconds to do. Right, so it has to get all the way to the thermistor, and until it's detected, then the error isn't going to be adjusted. So that means that what's really happening here is that the heater, which is the actuator to warm the heat, warm the air, is out of phase with the thermistor. Right, and that out of phase condition is what leads to oscillation, because when the temperature of the output is ramping up, the thermistor is not detecting it. When it detects it, it's already ramped up. So that now there's a response in the system, in the control system. So the delay, time delay, doesn't affect your gain, but it adds phase lag, because this isn't changing the ultimate value of MT, or the relationship between your error and the control action. What it's doing is it means that there's a delay, there's a phase shift, or an out of phase condition between the variability in our output, and which is measured by our sensor, and the true output, right? So if you like, it's almost like the output from here, right, is going to be the problem. Let's call that theta S. Right, so you get an out of phase condition between the true temperature theta, call that theta out, and theta S. These two are going to be out of phase with each other. So let's do an example. So this is just kind of trying to explain with this example, or this situation with our with our lab experiment of air flowing through a pipe, we're showing this is what's happening. That lag time is going to create an out of phase condition where the output is ramped up much before the sensor detects that ramp up, and so the sensor starts to ramp up out of phase. And of course, that sensor ramping up out of phase means that you have an out of phase error as well. The error here will also be out of phase, right? And so you kind of get this unstable condition. So let's look at this example. We're putting an actual system in place here, a system with the 0.2 seconds time lag, and it's a first order type 1 system that experiences this type of time lag. So we're going to analyze this using the Bode plot system, Bode plot method, look at the effect of that time delay. The tricky part that we haven't dealt with before is this term involving a time delay. This is the only tricky part really, because we can easily create a Bode plot for this transfer function if you didn't have this, right? But now you've got this. That's adds some complexity to it. But since we know that that is a pure time delay, we know how to represent it. We recognize that just gives a pure frequency response. Why do we say that? Because when we take frequency domain analysis, or when we use frequency domain analysis, we always do this. We substitute S equals J omega. So we're taking our S here, and we're putting in here J omega, substituting that. So it now becomes this term here, e to the minus J omega tau. And as you can see, this does not have a real part. It only has an imaginary part. So what do we know about a complex power to an exponential term? We know that complex power simply represents oscillation. It doesn't have any real part, so it doesn't have any reduction over time. It just has a pure and simple oscillation or frequency component. So this reinforces what we already know, that this is a purely complex contribution with no real part. And so that again reinforces the fact that because it's just purely complex, it doesn't have a real part, it's not going to affect the gain. But because it's complex and it has an imaginary part, then it is going to add this phase lag to the system. If we were to do this, then find the angle of e to the minus J omega. What's the angle or the argument of that term? Because we'd have to do this if we wanted to plot this term on our Bode plot. We'd have to find, well, we already said magnitude is 0 for all values of omega, but what's the phase lag or what's the phase angle for values of omega? Well, the phase angle by definition of our exponential term with the power of minus J omega tau is going to be minus omega tau, right, in radians, or if we convert that to degrees, it's going to be minus 180 over pi times omega tau. This is just the conversion. That means we could plot it now, and we can see what the impact of this term is. We have to know what our lag is. If we say it's 0.1 seconds, for instance, in this example, then just as we've plotted different terms, different elements in our Bode plot tables, we could do the same thing again. Our term is this. We're taking the angle. We don't need to do anything with the gain, because we said already there's no gain impact. But we're just looking at the phase angle now. The phase angle is going to be minus omega t tau 180 over pi, and we said this tau is 0.1. It's really going to be minus 18 omega over pi. Right, that's our phase angle. So we just substitute in different values of omega. You can see it's just a scalar. It's not complex. You'd have to take 20 log 10 of anything here, because you're not dealing with the gain. We'd have to take the tangent or inverse tangent of anything to get our phase angle. It's just yielded directly. So we just take our 0.1 and substitute it in there. So that means it's minus 1.8 over pi. Our 1 is going to be our 18 over pi. 2 is 36 over pi. But look what happens down here, and especially when we calculate out the numerical value of these, you see it starts with a very small value at 0.1 radian per second. It gets down to minus 6 degrees at 1, but then when you get to 10, it's gone to 57 degrees, and 100 minus 573 degrees phase angle. So you can see there's a sort of exponential, well, not surprising, it's an exponential term, right? But there's a very aggressive drop off. So if I was to just sketch that, you know, so if I say this is minus 180, and this is my phase angle here. No, let me do this better. Omega minus 180, 0, let's say minus 360, right? So this is the range I'm working on, and this is phi, my phase angle. And so we're saying at 0.1, 1, 10, and 100. It's a logarithmic scale, so evenly space the decades. And we know from what we see in the table here, we're going to have a point here at 1, we're almost the same. At 10, we're coming down to minus 57 degrees, so we're still up here. But when we get to 100, we're at minus 573, which is all down here somewhere. A big drop off, and that's what this function, pure time lag, does. It sort of falls off a cliff in terms of our phase angle for this particular system. So if we plot this system that we're looking at here, if we just ignore the pure time lag, it's 1 over s to 1 over s plus 1. Substitute s equals j omega, and then we can calculate our phase angle for each of these two elements. Very simple, because the 1 upon s we know already. Our phase without time delay, our pure integrator gives us minus 90 degrees for all values of omega. Why? Because we've got a 0 on the bottom here, so this is minus 10 to the minus 1 of infinity for all values of omega, which is minus 90 degrees. And our minus 1 upon our pure lag with a tau time constant of 1, so that means we're going to have more minus 45 degrees here. This is going to be approaching 0 degrees. It's not going to be exactly 0 degrees because it's 0.5. And then when we get to 10, we're going to be approaching 90 degrees. So I'm not calculating what 5 is. So these are the actual values, right? So I did my very rough estimate, not too far off. So we can see our phase line here, you know, and see the values of phase angle for different values of omega. If we plot that, done it using MATLAB here, then our magnitude plot, well, fair enough, our phase plot goes from minus 90 to minus 180, and it levels off at minus 180. So we have a phase lag that starts at low values of frequency of minus 90, and that lag increases through minus 135 to minus 180 as frequency goes to higher values. So we got all that. We've got these numbers already. So what we're going to do now is introduce this additional line, which is our pure time lag, and see what it does to the phase plot. Well, at low values again, it's minus 6 degrees. It's pretty small. And as you go to 1, it's minus 11.5, minus 57 at 5, minus 115 at 10. So when we add them up, we get our totals here. The difference there's no difference between having the time delay and not having the time delay in the gain plot. They should be the same, but with the phase, you can see the phase looks almost flat for the blue line, which is without the time delay. But when you introduce that pure time delay, it really just drops it right off the cliff here. Right, so that's the big difference between the two. So this is without the time delay. And you can see the scaling is totally different on the phase plot here. So the scaling is just this before 0 to minus 180, but we're now going down to minus 720. Alright, so that's the impact of pure time delay.